Hey guys, still Thursday, and we are still doing algorithms homework problems, and probably problems that you might find on an exam. So in this case, we are given a conjunctive normal form. It's all set up for us, and there are two questions that we want to answer, and we're going to roll them up into one. So first, if you were to create a graph from this, right? If you were to turn this into a graph, right? All the literals to vertices and edges between the ones that don't contradict and aren't in the same clause, would it have a clique of size k, where k is the number of clauses? And what would that mean if it did, right? So we'll answer that. After that, we're going to construct the complement graph of the one that we just made, and we're going to use the clique that we just found to determine what the smallest cover of the complement would be. Okay, and we'll go over all the, and just in case anybody's shaky, we'll go over all the terms as and when we use them, but not a moment before. So to start, turning this into a graph, how the hell do we do it? Well, there are two rules to follow. First, one vertex per literal. Alright? So we have 11 vertices because there are a total of 11 propositions being made here. Right? Up to 11. Alright? There are only 4 literals, but there are 11 versions of them. So 11 vertices. And these are all broken up discretely into their clauses, right? So each clause, like so, and we're going to label them appropriately because it'll make things much easier. X1. So right now, just in case, you know, we're following from here. It's a one-to-one mapping, so you can see what the pattern is here. So now we have our vertex set, and the rule, as I said before, is no intra-clause edges. So if you have vertices that are in the same clause, they cannot connect to each other. There are no edges to be built between them. And if two vertices contradict each other, no edge between them, because these are propositional. We're trying to get true-false values, and if they contradict, then we have problems. Also, if they're in the same clause, it's a problem because this is meant to compare these, so they shouldn't be touching each other. They should be separate. Okay, so we'll start from the left and go to the right. In general, we're not going to be going backwards ever. Like, you're not going to get to x2 and look back here because you've already been here, right? So if anything's connected to x2, we know because we already did it. So we only connect forward, and we're just going to move clockwise around and make all the edges that we need to, and it's going to be a lot of edges. In fact, I may actually just break out the colored markers because you may not fully understand yet how many edges. All 3 at once. So x1 cannot go to x1 complement, so we go to x2. And we go to x3. And we can go to x1. That's good because they don't contradict. We can go here. We can go here. We can go here, and we can go there. And that'll be x1. We'll do a different color for each clause. How about that? x2 complement can go to x1 complement. It can't go to x2, but it can go to x3, so that's good. It can go to x1. It can go to x3. x2 complement cannot go to x2, but it can go to x3 complement. And it can go to x4 everything can go to x4 because there's no other one. So, yeah, here we're good. x3 can go to everybody over here. Can go to x1, but it cannot go to x3 complement. And it can go to x2, not to x3 complement, and then to x4. Now, x1 complement cannot go to x1, but it can go to x3. And it can go to x2, and it can go to x3 complement, and it can go to x4. x2 can go to x1, and it can go to x3 complement. That's good. x2 can go to all of these. x3 goes to x1, but not to x3 complement, and it goes to x2, but not to x3 complement, and it goes to x4. So that's that one done. And now we just have this. We have less and less to do every time. x1 goes to x2. x1 goes to x3 complement, and it goes to x4. x3 complement can go to everybody down here, even x3 complement, because they agree with each other. They like agreeing. And I forgot to use black for the third one, but we'll make do. So, does it have a clique of size 4? That we can eyeball, and just in case, I promised that we would go over all the terms. A clique is a maximally connected subgraph. So if you have a set of vertices, you have a set of vertices V, there will be some V prime in V, some subset of V, V prime, proper subset, or not, that is maximally connected. So a maximally connected graph is like, that's a clique of 2, and this is in some bigger graph, right? We don't know what's happening out here. That's a clique of 2, right? They can't be more connected than that. A clique of 3 looks like that. It's just a triangle. Clique of 4. Right? And if you want to be annoying, like there's a clique of 1. So we're looking for a clique of size 4. Are we going to find one? Well, here, okay, good. Let's break out the black. The black will have its day. So we'll start here. x1 to x2, from x2 to x1, and from x1 to x2, and from x2 back to x1. But they're not maximally connected yet. So we want to see from here to here. Yep, and we've got it. There it is. Right, because these, it's kind of a wacky setup here, but yeah. So these edges are all crisscrossed in the representation here, but this corresponds to a clique of size 4. So we found a clique of size 4. So there's that. So what does it mean that we found a clique of size 4? If we found a clique of size 4, that tells us that the CNF is satisfiable. So let's take a look at what we found. x1 to x2 to x1 to x2 again. So we have x1, x2, x1, x2 from C1, C2, C3, and C4. Okay? Each one. And they're all connected completely. Alright? They're fully connected. that means that with these variables, we should be able to just eyeball and divine some solution that would allow this whole thing, this whole conjunctive normal form, to evaluate to true. And in fact, the first thing that we would try as a computer would work. We would set everybody to 1. And it works. Right? So we have x1, it's true. These are ORs, so we don't care about anybody else. This is true. We have x2, true. ORs, nobody cares, so this is 1. True. x1 again, true, it's good. x2, it's not complemented or anything, so it's true, so it's good. This whole thing evaluates to true. And everybody's happy. So that's an important takeaway. If you make a graph from a CNF and you find a clique, the CNF is satisfiable, and you found the literals that you would need to manipulate in order to satisfy the CNF. But it tells us something else as well. So remember the rule that you cannot have edges between vertices from the same clause. So in a certain sense, it's like we're treating every clause as a vertex. So in a way, it's kind of like we've got a graph with 4 vertices. Kind of. So, given that we found a clique of size 4, that actually means that we've found the largest clique. There's no bigger clique in this graph. There may be other cliques of size 4, but they're all between 4 vertices. So no matter which way you slice it, you're only going to get a clique of size 4 at most. Okay? Now this is where things get a little interesting. Let's get rid of all this mess. In graph theory, we have a theorem which states that you have a set of vertices V, and you find a clique V prime in V, then V minus V prime is equal to a cover. It's important to make that distinction. A cover. Not the smallest or not the largest, although the largest cover is... Well, what's a cover? I forgot. We're going to talk about the terms. A cover is a set of vertices... No. A cover is a set of vertices that touches every edge in the graph. So if we have something like that, let's say it's connected like so, a cover here would consist of all the edges you need to touch every edge in the graph. So obviously you could just say, oh, well, it's V, fuck you. And no, we want the smallest one. Well, we have an edge here, so we know that we need this guy. We know we need him because he has the highest degree of anybody. We know we need him because otherwise we can't touch this edge. We don't need him because these edges are all covered. This edge is covered, and we need him. So that's your cover for this graph. Okay, so hopefully that makes sense. Right? It's a pretty simple definition. It's just the set of vertices, like it doesn't have to be minimal, but it's more fun if it's minimal. Let's call it the minimal set of vertices such that every edge in the graph is antecedent to the vertices that you selected. Good. So if you take the set of vertices and you subtract the largest clique, or any clique, some clique V prime, in our case it'd be the largest because we know that we found the largest, we understood that, then you have a cover of G complement, the complement graph. So what's G complement? G complement is just if you have G VE, G complement is the exact same graph with all the opposite edges. So the edges that aren't in G are in G complement. That's all that changes. It's the same set of vertices, but just the complement. 1 minus C. So let's say that we had our graph from before, the one that I deleted, and we made G complement, what would be the smallest cover, given this theorem? The smallest cover of G complement, right? So we know that we found right? Because of the properties of the CNF, we know that we found the largest clique, right? We're not going to find a bigger clique, V prime, to subtract from the set of vertices. So that means that when we do subtract that number, we're going to get the smallest value possible left of V. So we're going to have the smallest cover. So we found the largest clique already. So V minus V prime, let's do this properly and call it cardinalities, is going to be equal to the minimum vertex cover of G complement. And in this case, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 vertices total, minus 4, the number of clauses, 7. So that's your answer. You're done. You don't have to construct G complement to figure that one out. If you want to actually construct the set of vertices, then you might have to do it. But if you're taking the exam and the question is just what is the size of the minimum vertex cover of G complement, that's how you'd figure it out. And that's that. Alright, so one more problem left for tonight. Up next, we are going to build an algorithm to discover or divine, whatever you like, the minimum vertex of any given tree. So that's up next. Have a good one, guys.